So, welcome to Microsoft Research for those of you who are not normally here, and for those of you who are, then welcome again. I just want to say a few things about our sort of Optics for the Cloud initiative. This is something we kicked off around about 6 to 12 months ago. And this is actually the first in our series of public lectures, if you like, in this space, where we've invited experts, Mark to start with today, but we will around in the sort of photonics optics space within the UK. And a lot of people, I think, are thinking, well, why is Microsoft Research doing this? We made a conscious decision probably about 3 years ago now that actually there was going to be a big role for optics in the cloud. And this is sort of driven by the fact that as a company now, we control everything from the sort of the devices, the hardware, right the way up to the sort of software stack that we use within the cloud. And for us, this is a real opportunity to rethink about how we do things. So, for example, we already use a lot of optics as point-to-point communications link within our data centers, but we kind of buy them in as black boxes. And now that we've got the sort of full end-to-end control, it was a real opportunity to think about, could we actually use optics in a way that was even more efficient than what we do today with the sort of black box optics, by understanding more about it. And so within the lab, we actually brought in a lot of kind of optical physics people, optical engineering people, and then we've kicked off the sort of optics of the cloud, where we're trying to engage with the wider UK community. And that's really what this is about. In fact, if you look at photonics, the UK is a really strong place in the world for photonics, and that's why we think this is actually a really good place to do this. And so even within the lab at the moment, we've got projects where we're looking at optics for networking, we're looking at optics for storage, and in fact some of these you will have already seen, I suspect, in that space. So it gives me great pleasure to welcome Mark Neal from Imperial College in London. He's a professor there in the photonics group, and his research interest is in microscopy and imaging, and in particular how we can manipulate light using software to actually really significantly enhance these imaging and microscopy applications. And so I'd like to now hand over to Mark Neal. Thank you.
Okay, thank you very much for the invite and the introduction. I'm going to talk about structured light and what it can do for us to improve the images we get out of optical microscopes. So some of this is unashamedly all about bioimaging, but some of the ideas can cross over into other aspects of optics and hopefully give some of you guys here, for instance, at Microsoft, ideas about what you might be able to do. Okay. And this on the right, it shows you the sort of imagery we're trying to get. This is a very old image. I think this is taken back in the 90s somewhere. Okay, so I've been working in this area for over 20 years now. But it's a three-dimensional representation of a transistor, which has been imaged with a light microscope, where we can measure the surface profile of that transistor in X, Y, and Z, and get imagery at the same time. So the color indicates height, and the textures you see there are basically the imagery we get from that microscope. Okay, so that's the sort of thing you can get out of these kind of systems. So really, what I want to start by doing is saying, what's the problem we've got with a normal microscope? So here is an example of an image you might see down a normal microscope. As you can see, there's some bits which are clearly in focus, and there's some other bits which are out of focus. Doesn't look very interesting image. We can't necessarily gain much information out of that kind of thing. What we'd like to turn it into is something which looks like that, where we have a very much better view of what's going on. We have an in-focus image of the whole object at one time. Okay? So the idea is we want to get rid of the out-of-focus blur. By doing that, we can increase the contrast in our imagery, and hopefully we can also, if we have lots of images at different focal positions, we can build up one of these sort of images here, which might be the sort of, starting to look a bit like you get out of a scanning electron microscope. So what's the problem with optical microscopy? Well, if you want to image things which are really small, you've got to use a high numerical aperture objective lens. Okay, and the resolution you get out of a high numerical aperture objective lens, delta R, is approximately lambda divided by the numerical aperture. Okay, so that's simple. You want high resolution, you use high numerical aperture. The problem is, if you've got a high numerical aperture, you've got a small depth of focus. So your depth of focus actually goes as refractive index times lambda, the wavelength, divided by NA squared. Okay, so that's the big problem you've got. So the stuff in your image, which is out of focus, doesn't really contain much information. It's blurred, it has low resolution, it just gets in the way. Okay, what you'd like to do is remove that out of focus light to leave you with the in focus, high resolution part of your image. Okay, you're increasing the contrast by doing this. You can measure your position in 3 dimensions because you can see the bits of the object which are in focus, and you know therefore where they are in that 3rd dimension. And actually, one of the things we're going to show you can increase the resolution that you're seeing down your microscope. So this is the outline of what I'm going to talk about. So structuring your illumination to get a better imaging. The classical way to do this is a confocal microscope. So that was been around, or the ideas have been around since the 50s. Okay. What I'm going to talk a bit more about is I'll introduce you to the confocal microscope. So we'll go through some of the features of the confocal microscope, what it does in terms of sectioning, what it does in terms of resolution. Okay. And then we'll look at about other ways we can do this. So can we do this by structuring our light in different ways? So a confocal microscope is a structured illumination system. We illuminate with a point of light, and we have a point detector. We're going to look at other ways of doing that. So parallelize a confocal microscope. Perhaps we can do it without a laser. Okay. Also, we can project grid patterns onto an object. Can we look at the grid patterns we get back at the object and gain some idea about what that object is in 3D? And that's what we call optical sectioning, structured illumination. And we could even get better resolution out of doing this, which is what we call super resolving structural illumination. Then I'll come and summarize some of the ideas I've gone through. So here's a confocal microscope. The idea behind it is you illuminate with a point source, you focus that down onto your object, you collect light back through the same lens onto a point detector. So these are 2 pinholes, that's illumination pinhole and a detection pinhole. Okay? And when your object is in focus, in the focal plane, you get a strong signal through onto your detector. If your object is out of the focal plane, right, the light from this dotted line comes back and it's defocused at the detector and you get a weak signal. So generally, what you'll see in that detector, if you were to scan a fluorescent plane or a mirror even through that focus, is as it goes through the focus, we have a weak signal outside focus and a strong signal inside focus. Okay. So what this has done for us is the pinhole has done something very clever. It's blocked the out of focus light. We no longer detect it, right? As a result, we just see the in focus light. We've got enhanced contrast. We can see where that's coming from in 3 dimensions because we know where the position was when we saw the object. And actually, as I'll show in a minute, this gives us some enhanced lateral resolution as well. Okay. So actually, I think I got it wrong there. It's 1961 Minsky patented these ideas. Okay. Actually, it wasn't until you got the laser that this became really successful. Okay. So the big problem here is how do you get your light through this pinhole here? If you've got a laser, you can get lots of light through that pinhole, and everything's hunky-dory. Okay. So it's made successful by the laser. The other problem you have is you're only measuring a single point in your object, so you have to scan the beam to build up an image, but a positive thing, you only got a single detector. It's relatively easy to detect the signal coming from that single detector, and people were building microscopes using this technique in the 70s and 80s, It's relatively easy to acquire that signal onto a computer. Hello.
Yeah, I was thinking like you mentioned that enhanced contrast is enhanced resolution. So
No, I haven't yet.
Define contrast and how you define resolution.
Well, I think we'll come on to here in terms of finding out where the resolution enhancement comes from. Okay. So you can acquire stuff onto the computer, and that means it's relatively easy to add extra processing steps should you want to do it. Okay. You can find applications. You can put a reflective material in there. Material scientists like it. They can look at things like transistors, which I showed you before. Another thing which medical scientists like is to label their samples with labels which identify particular functions, and therefore you can work out what's going on biochemically or chemically within cells and tissues. Okay? And actually you can get pretty good images, just a few tens of photons per pixel. And this shows you just one type. This is a Leica TCS SP5. Okay, that's probably about a 10-year-old system. The box here has got full of lasers. That's the actual scan head where you're scanning your beam using scanning mirrors. Okay, and here's your normal microscope stand. But there's all sorts of manufacturers make them. Here's some example images. You can just download these off of manufacturers' websites. So there's Leica Microsystems. This is a multi-labeled image, okay, of some sort of tissue. A Nikon one where there's a single label, but it's looking at parts of neurons. I think these little blobs here are dendritic spines. And here's an example of material science application from Zeiss, where they're just using it to help them map out a three-dimensional structure. Okay. So the idea behind resolution coming from that, and I don't think it's the enhanced contrast that gets you the resolution. It's something inherently in the way the system works itself. Okay, so the way it works is that you, well, what we have to think about is we can look at what we call a point spread function. So the point spread function tells us what the image of an infinitely small point looks like. Okay. If we are to image an infinitely small point conventionally, okay, and this is what our image might look like as we were to move it up and down in focus, the point up and down in focus, okay, we see in the focal plane it's a bright blob, out of focus it gets dimmer, and it also gets more diffuse. Okay, now this is something which is limited by diffraction. It's limited by diffraction because it's the numerical aperture, which is actually the size of the size of the lens, the angle of rays that come out of your lens onto your sample, which limit that diffraction, and it limits the size of that point spread function. So if we have a point spread function here, you're probably getting about the full width half maximum is about half lambda over NA, okay? So it's probably about the order of 250 nanometers in typical optical wavelengths, okay? And you also have a resolution in Z, so a single point actually optically sections itself, okay? It gets dimmer out of focus, okay? You probably have that's probably of the order of 700 nanometers. So, what happens when you have a confocal point spread function? Well, you have if you have your point sat in the image plane, the probability of you getting light back from that point is equal to the probability of you managing to actually hit the point with your illumination, multiplied by the probability of you being able to detect light coming back from that point. So the net result is actually the confocal PSF is the product of the illumination PSF and the detection PSF. So if you assume those are roughly the same type of size, okay, then the confocal PSF is the square of this one, okay? And if you're squaring that, it's generally getting smaller. It's getting smaller by about a factor of √2 in each dimension. So you're probably going to get of the order of 150 nanometers minimum, full width half maximum the size of that blob there, or 580 going in the axial direction. So this is where you're getting your resolution enhancement in a confocal microscope. So this, again, I'll put some other provisos on this. This assumes you have an infinitely small pinhole. Okay? The problem is you have an infinitely small pinhole, then you're going to lose light. You're not going to get any light through it. So what you will tend to do as well is you make that pinhole a bit bigger to get more light through it, and you make some compromise on the size of that PSF. Okay? So there's another way you can think about the resolution of an optical system, and that's via its optical transfer function. So the optical transfer function tells you how a pattern gets imaged by your imaging system. Okay? So we do it as a function of spatial frequency along the x-axis here. Okay? 0 spatial frequency is a uniform pattern. Okay? As we have a finite spatial frequency, that is essentially a sinusoidal image. Okay? The higher the spatial frequency, the higher or the smaller the fringes on this grid pattern, and as a result, you can see that this represents finer details in your image. Okay? So what I've plotted here actually is a function of various different defocuses, but this is an ideal incoherent imaging OTF, okay, for a perfect lens. So you can see it drops off and gets smaller and smaller. Okay, that might sound alarming at first, but actually this is the way your eyes work, and that's what makes images look natural. Okay, so that's what makes images look natural. The other thing to note is there's a cutoff down here, right? That cutoff is at 2 Na over lambda. Okay, and what this is saying is your simple imaging system cannot see spatial frequencies greater than that 2 Na over lambda. Okay, so that's the fundamental limit that's determined by diffraction. So how is that OTF related to our PSF? Well, they're all related via Fourier transforms. So Fourier transform is what turns you a time signal into a frequency spectrum, or a spatial signal into spatial frequency spectrum. Okay, so we can think about Fourier transform as transforming from real space to Fourier space. If you have an image and you Fourier transform it, it tells you what spatial frequencies are in that image. If you have a point spread function and Fourier transform it, it tells you what your optical transfer function is. So your optical transfer function tells you what spatial frequencies in your image you're allowed to image or get imaged, and therefore it tells you what your image looks like of your object. So if you have your object, Fourier transform it, multiply it by the OTF, inverse Fourier transform it, that tells you what your image looks like. Okay, so why is this important? Well, we can take that into 3 dimensions. I showed you an OTF in 2 dimensions. In 3 dimensions, our conventional point spread function looks like this. If we Fourier transform it, we get this funny sort of donut-shaped thing. Okay, if we plot that as cross-section through that donut, okay, these are horizontal spatial frequencies in this direction. These are axial spatial frequencies. There is this missing cone here, so that's what's happening in there. That missing cone is why we can't section with a normal optical microscope. Okay, and that's telling us that if we have a flat plane, our flat plane stays just as bright and looks just the same as we move it in and out of focus. Okay, it's only by having something like some sort of structure in what we're looking at that do we start seeing that attenuate with defocus. Okay, so that's what we're doing by producing our confocal system. Okay, we're putting some structure into our object so that when we image it, we're not seeing just this point spread. We're seeing this smaller point spread function here, but if we Fourier transform that, we see a much larger region of support. Okay, so the region of support is the region where you get non-zero values in your optical transfer function. And actually that yellow line indicates what that region of support is. So we can now measure all these other spatial frequencies. We've filled in that missing cone, right? And we can now see these extra spatial frequencies. Outside of there, we cannot measure those. Okay, they're still measured. They're still restricted by diffraction in this case. Again, if we look back in 2D, okay, this is that blue line here, but I've just plotted it and plus and minus spatial frequency here. Then you can actually see that our confocal optical transfer function is wider than our conventional one, so we can measure higher spatial frequencies. We can, in theory, go all the way up to 4, right? But actually, it's pretty small, above a factor of 3, about spatial frequencies of 3. So it's okay, but it's not great. So that's how confocal microscope works. They've been around since the early 60s. You know, practically speaking, they've been around since the late 70s. Okay, commercially, you've been able to buy them seriously since the early 90s. So the question is, can we improve on that confocal microscope? So what are the problems? Well, one of the problems is you've got to scan a spot across your sample. Yeah.
Yeah, coming back to that, like, so how do you define contrast in terms of PSF, and then how we compare it with results?
Contrast, I'm really defining as some sort of subjective measure here. Okay, so it's a subjective measure in that you have less blur, so you see more contrast. So a lot of the way people might think what entails an improvement in an image is whether you see more details, and you're seeing more details because you have less blur obscuring those. Okay, so you can come up with proper objective measures of contrast, but in a way, I think it's easiest at the moment to think about subjectively what constitutes better contrast. Yeah.
I was thinking, like, if you define in terms of, let's say, like simple, like signal to noise ratio, and then like how would that relate with a smaller?
So we'll talk a bit about signal to noise ratio in a bit. Okay, and actually that's one thing a confocal microscope is very good at, because it's blocked the light which is out of focus completely. Okay, you never detect it. So how can we make a confocal microscope better? Spot scanning slow. Can we make it quicker? Lasers, potentially expensive, limited wavelengths, bit awkward to use. Okay, can we use cheaper conventional light sources? And the other one is the resolution's limited. We're still limited by that factor of about 3. Okay, yeah.
So I want to say something because I think it's a misunderstanding.
Okay.
It feels like confocal, I got a 40% improvement
Yeah.
in resolution. Doesn't feel like a lot.
No.
But then you drew a picture with like a big missing triangle and filled it in, and that feels like something more.
Okay. So if you were to look there, so this is what I'm plotting here is the region beyond where you have non-zero values in your transfer function. Okay, that's effectively this yellow line here. That's giving you the outline. So inside here it's non-zero, outside it's 0. But the downside of that, as you can see, is actually it's pretty 0 for large proportions of that. So we're not really seeing that we're not getting that full benefit of the improvement in resolution. Okay, so some of the techniques we'll talk about later, you get a much better benefit in that you can actually fill this region out here a lot more effectively.
And not just that, but if you go to the previous slide, it's also this kind of funny shape, this donut shape.
Yep.
Is there a qualitative advantage for having the stuff that's inside the black triangles at the north and south?
Yes, because that's effectively, so if you think about out of focus stuff, right? So it's low spatial frequencies. So in the transverse direction, it's things which don't change very quickly, okay? And what it's saying is that we don't see those change. If they change in the vertical direction, we can't see that, right? So if they're changing in the axial direction, we can't see them going in and out of focus. So that's really what it's saying. So that's what this missing cone is telling you. It's saying that things which may have, large extent laterally, right, and therefore low spatial frequencies laterally, if they're changing quickly in the axial direction, we can't measure that. Yep. So even if it's an infinitely thin sheet, as it moves out of focus, it still looks the same. Yep.
So if these are like low frequencies, so how would like filling the missing cone would lead to increase in resolution, because high frequency should contribute to the resolution, right?
All frequencies contribute to the resolution. I mean, it's about the contrast again. Okay, so it's not about filling this. Filling that cone isn't about increasing the resolution, apart from the fact that we do get better resolution in the axial direction now. Okay, so we can determine where things are in the axial direction better. Okay, the lateral resolution is all about filling these regions out here. Yep. So, can we make it better? So, Petran in late 60s came up with the idea of a parallelized confocal microscope by building, taking a Nitkoff disc. So, a Nitkoff disc is a spiral array of holes on a disc, right? It looks like a bunch of parallel confocal microscopes, okay? You're effectively shining light through these pinholes, imaging those pinholes onto your object. Light gets the image that's emitted by the object or comes back from the object, gets imaged back through the same pinholes, okay? And you get the same confocal effect, okay? Except now you've got many pinholes in your field of view at the same time, okay? You use a camera as your detector instead of an imaging detector, instead of a single pixel detector. The downside is you have to place those holes sparsely to avoid crosstalk. Okay, so if they're too close to each other, as out of focus light from out of focus parts of your object would fall through neighbouring pinholes, and you'll get a signal at your detector. Okay. You can use a non-laser source for this, but it's still relatively inefficient. There have been more recent developments which have used microlenses to focus laser sources into them, which are a lot more efficient. Okay. But is that crosstalk a problem? So this is one of the ideas we came up with back in the 90s and said, well, okay, let's live with the crosstalk, right? We know that if we put our pinholes too close together, we're going to get crosstalk from one pinhole to another pinhole. Out of focus light will still be present in our image. However, in focus light will be brighter than out of focus light. Okay. So we still have some sort of confocal effect, and that is effectively if we're using a random mask and shining that onto our object, the light we get back, or the image we get back through that random mask looks like a composite image. It's a composite of an out of focus image and an in focus image, an in focus confocal image. Okay. How do we get rid of the out of focus image or the conventional image? Well, we just illuminate our object with a blank sector. Okay, you illuminate with a blank sector. We now have two images. We'll take them sequentially. We take an image here and another image there. We synchronize the disk to our camera, so we know that this frame takes this image, another frame takes that image, and you calculate the difference between those images to extract just the confocal image. Okay, and that's what you display. Here's some examples. So this is a fly's eye. Okay, the fly's eye has a region which is in focus, and you can see in the composite image it's brighter in that region that's in focus. In the conventional image, we don't see that brightness. We can subtract one from the other to give us an optical section. Okay, you can then build up a number of these optical sections. You can do a number of different tricks. You just even just adding the light up from those different optical sections gives you what's called an autofocus image. Okay, and there everything now looks in focus at the same time. So that's how the system works. Here's some other examples. This is soot. We thought we'd image soot because someone had some soot. It's very black. You wouldn't think you're going to get very much out of it. Actually, when you look at soot down a microscope, some of it's quite interesting. And here is an image where we've rendered it. Again, this is just a reflection image. We've rendered it according to the height of the features in that soot. So the colour is height in there, and then the image is what the soot looks like. But again, this whole system will work with fluorescence. And fluorescence actually is where a lot of systems are most interested, the biologists are most interested in using these techniques. Do you even need a random pattern? Actually, you could get away with just a grid pattern. Okay? A grid pattern, in many respects, works just as well, if not better than the random pattern. Okay? It's very difficult to average out a random pattern to give you exactly half. Okay? It's very easy to average out a grid pattern to give you exactly half. Okay? The important thing is this still works because that grid pattern disappears as you defocus the image. So you're finding a grid pattern onto your object. As you defocus the object, your grid pattern goes out of focus as well, because it's subject to the same rules of defocus as other. It's a single spatial frequency, if you like. It's subject to the same rules of defocus. Okay, so actually, this, in many respects, looks better, and it reduces a bunch of other artifacts. Actually, these things are in use now. We set up a spin-out company called Aurochs. We actually make a unit now which sits inside a Carl Zeiss SmartProof 5. So if you want to go and buy one, you can go and buy one. This is their system. This is from their advertising blurb. It uses a 405 nanometer LED light source, so there's no lasers. Okay, this is the sort of images they produce out of it. So here's a materials science. This is really a materials science applications machine. Okay, this is a milled aluminium surface, and what they're managing to extract is the surface profile along that milled aluminium surface. Another important application is looking at solar cell surfaces. So solar cells have a structured surface in order to reduce reflectivities and enhance the absorption of sunlight. So they're interested in are interested in applications where they're looking at particularly those surfaces like that. Okay? So that's all based pretty much on this idea we had in '98. Okay, so we're still making those devices now, and they're going to Zeiss products. This is another application. This is now another Aurochs product which uses the same sort of ideas, okay, but it's for fluorescence. Now here with fluorescence, we want to be able to make as much use of the light as possible, okay. We use a mask, right, which is just line patterns, okay, and this line patterns is rotating around on a disk. The disk is actually sitting here. What we do that's slightly different now is our input light comes through here. That's the exciting light path. You image your grid pattern from your disk onto the object. Light comes back from the object onto the disk. Where the grid pattern is still in focus after that double pass, you get a large amount of light through. Okay, so this path here consists of a conventional plus a sectioned image. You also capture the light that is reflected off the disk. Okay, so we're trying to make as much use of the photons we've got coming back as possible. If it's reflected off the disk, the light, when it's in focus, just hits the white areas, nothing hits the black areas, which are reflective. Okay, so we get a minimum of intensity. So in this reflected image, which passes through there, we get a conventional minus sectioned image. Okay. We capture those two images at the same time, and in fact they're projected onto a single camera. Okay. So this is also an advantage over this sort of system. Here we capture images at 2 different points in time. That's not particularly a problem when you're looking at milled aluminium surfaces or solar cells, because they don't move. It's a problem if you're looking at things which are biological, because they do move. Okay, so it's the same processing algorithm. We just have to subtract one image from the other, and we're left with a confocal image. So here's some examples of the types of devices, the types of images you can get out of it. That's the unit. It's quite small. It uses LED or lamp sources, a single CMOS camera, bolts on the side of a standard microscope objective, and we can get images which look pretty similar to what those you get out of a laser scanning confocal microscope. Okay. This is the latest version they're building, which is all in one. So this is a box which sits on your lab benchtop. So you can see some other bits of kit you might find on a lab benchtop. It has everything in it that your microscope would have. It has a motorized X, Y, and Z stage. It has multiple color LEDs as sources, so you can switch them on and off very quickly. Dual 4 megapixel CMOS cameras. So that's the sort of state-of-the-art people are using now for bioimaging. Compared to the previous ones we used 20 years ago, those are probably 1/4 megapixel cameras. Okay. There's also a computer in there. That computer has to take care of acquisition, processing, data storage, and also streaming results to an external display, which might be on an iPad. The challenges in building this actually are not the optics anymore, right? The optics is 20 years old. The challenge in building this is the automation, the image processing, and the data handling. How do you handle all that data coming off of your cameras that quickly? How do you process it? How do you get it to where you want it to be? Okay. So here's some examples. An example of a stained kidney section. So this is a standard type of example slide you can get, which is pre-stained. It has 3 color stains. We've got an image here. It's a stack. It's chopped into 50 sections, 3 color channels, LED illumination. So the LEDs are being switched on and off, and effectively this takes 11 seconds to acquire. Okay, and so we have something which is a stack through in Z. Okay. But it also highlights the problems. That, if you do the maths, that's 2.4 gigabytes in 11 seconds. With that data, we have to process that in real time. We have to do elastic registration because we have to put 2 images on 2 separate cameras, and we have to subtract one from the other. We also want to stream that to an external display, or even save it to disk if not in memory. Okay. So those are the sort of channels we have. Those are the sort of challenges now that we have in building these kind of systems. It's almost more the computational challenges than it is the optical challenges. Okay, so let's have a think again about how that system will work. So here's our OTF diagram again. These are our grid patterns, okay? Now what also, the other graphs on this, lines on this graph, is actually what the OTF looks like as you increase the defocus in the system, okay? So we see here, for a conventional imaging system, our uniform object, right, as we defocus, we still see the uniform object because the OTF is still high, okay? If we look at higher spatial frequencies, however, as we increase the defocus, the OTF drops pretty quickly. Okay, so what that's telling us is that these get dim pretty quickly. Okay, and that's the mechanism behind how that spinning disk system works. It's also the mechanism behind this other technique, which we're going to talk about, which is grid projection structural illumination microscopy. Okay. So here, if we think about a camera looking at an object, what that previous graph is going to tell us is that that object, if it's a spot or a grid or a sheet, in focus it will look like a spot or a grid or a sheet. Okay. As we defocus, the spot of light gets bigger and blurs out. That's why a confocal microscope works, right? The grid gets dimmer, okay? The sheet looks just the same, okay? So we move further, we can virtually no longer see our spot of light. Our grid has got very low contrast, okay? But our sheet still works, still looks the same. So that's what happens if we look at an object which has these patterns. What if we take an object which is a plain sheet and illuminate it with these patterns? So our illumination is some sort of patterned illumination. It could be a spot, it could be a grid, or it could be uniform illumination. Okay? The same thing happens. As you move the object, the spot gets bigger and defocuses, right? The grid loses its contrast, but the sheet illumination, it just stays the same. Okay? So the idea, you can see the idea here is, in fact, our previous, this is why our spinning disk microscope works. We're actually then pass the image we get back here through our disk. Okay, in focus we get our bright lines in our grid pattern here, pass back through the holes in the grid in the disk. Okay, out here, half the time it hits the holes, half the time it hits the reflecting surface. But there's another way. You can look at this now and you can say, well, actually, we don't need that disk to do the detection. We could do it by looking at the image. If we look at the image, we can see with bits which are in focus will have a grid pattern superimposed on them. Okay? And the bits which are out of focus won't have a grid pattern superimposed on them. So you can build an optical sectioning microscope just by projecting that structural illumination onto the object. So here's our structural illumination. We can see that structural illumination on parts of that object. Okay. The question is, how do we make sure we can see it all the time? Okay. Maybe it's not going to show us. But the way you can see it all the time, or the way you can tell it's there, is you move the grid pattern. So if you move the grid pattern, right, you'll see the grid pattern moving on your object. So what you can actually do is you can move that 3 different positions, grab your images with the CCD camera. The grid pattern is only visible in focus, right? You then have to select and find out which bits of your image were moving with post-processing and software. So if you were to just add up those 3 images, you get something which looks uniform. Okay, it just looks like a conventional image. What we do is we look at the RMS variation effectively. Okay, if you look at the RMS variation as you move those grid images, you get a sectioned image. Okay, so this is how we can get sectioned images by processing those images in the computer. Here's some example images. So this is another fly's eye image. Okay, we're just looking at a single section. Here's a macroscope image of the parts of a watch, and that's actually a summation over multiple sections. And I think here's that pollen grain again. So that pollen grain was taken with this system. Okay. There are some issues you can see here, or maybe we'll talk about some of those later on. It's quite difficult. The contrast is quite high on this display, but you can see some other artifacts out of focus. Okay. Here, one of the big problems you see with the reflection system is that where we're reflecting light off of surfaces which are angled away from our collecting lens, we don't see the light coming back anymore. Okay, so it becomes a bit difficult to see there. So those are examples. We even got a bit cheeky. We did it with a candle as a light source back in the 90s again. Okay, you can build optical sections using a very, very weak light source, in this case a candle. Okay, the biggest problem is actually flicker on the candle, but perhaps you can start seeing some of the issues here we have. Another big problem with these kind of systems is noise. Okay, so if we look, here's another example. This is fluorescence again. We could take 3 images. Those 3 images have got the grid position in 3 different positions. We can add them together. We get a conventional image. We look at the RMS variation. We get an optically sectioned image. Out of focus, our conventional image just looks like a horrible blur. Out of focus, our sectioned image looks quite nice. And it looks quite nice until you actually rescale that image. And the problem here we have is we're looking at differences between signals we've detected. So with differences between photon signals we detected. When you detect photons, you get shot noise. If you, in a finite amount of time, if you expect 100 photons to arrive, you're going to get 100 plus or minus 10 photons. Okay? So there's always an uncertainty on how many photons will actually arrive, and the problem is you can't get rid of that. That shot noise is something you can't get rid of. When you take 2 images away and they both have shot noise, you're still left with just the shot noise. So that's the issue we have here. We have some shot noise. That's one of the problems with these subtractive imaging techniques, which a confocal microscope does really well on, because it blocks the light and you don't detect the shot noise in that other image. So that's another system which was commercialized. So it was Keyoptic had a system called OptiGrid, used conventional light sources. These were very simple. You can see how simple this is. This is a simple piece of kit, right? You just put that in the illuminator of your microscope, and you've got a camera on the other end and a computer, and you've turned it into something which can get optically sectioned images. Okay? So the size of this, compared to what the size of your confocal microscopes were before, was very, very small. Carl Zeiss produced their own version of this, and I think you can probably still even buy Carl Zeiss Apertones. But again, there's some issues. Noise is one artifact. Another artifact is because we have a grid in a fixed orientation, we get potentially artifacts due to that grid. A third artifact is because we're looking at changes in the image. As you move the grid, if your image moves, you get artifacts due to that. Here's some examples of the sort of imagery that those systems can produce. Okay, so here's an example. One of the big advantages of all these is you can get a conventional and a confocal image at the same time for free. Okay, you can render it all in 3 dimensions. Here's something just looking at an autofocus image of something which would have a lot of blur in it normally. But is that as good as it gets? Well, that's our calculation. It's an RMS calculation. It's a bit non-linear, okay? We've got a square root in there. So calculating what the OTF for this thing looks like is a bit difficult. And what that means, it's potentially a bit difficult to understand what you're actually looking at. We're also throwing away the phase information. So we had phase in there, and we're throwing that away. The phase is telling us the position of the grid in those 3 different positions. Okay? We're throwing it away. That actually makes it very easy to process, because we don't have to worry about what the phase is. Okay? This is agnostic of what the actual position of the grid is. We don't care. But Mats Gustafsson, in the early 2000s, showed how you could use that phase information to get better resolution. Okay, so super resolving structural illumination, or SRSIM. Well, it's the same sort of idea. We've got a grid pattern. We illuminate our object with it, so we're multiplying the object with the grid pattern. The grid itself has 3 or more define spatial frequency components. It's an intensity pattern, so it would have a DC, which is your offset, okay, and a positive and negative to do, if you've got a cosine, this is the e to the I theta, and this is the e to the minus I theta component. Okay, so that's what you get out of a simple grid pattern. But what your camera now sees, right, is a copy of your object spatial frequency spectrum placed at each grid spatial frequency spectrum, right? So you've multiplied your object with a grid pattern which has this spatial frequency spectrum. Therefore, the spatial frequency spectrum of what comes back from your object is the convolution of this with the spatial frequency spectrum of the object. Okay, so if that's your original spatial frequency spectrum of your object, you get copies of that on top of those other grid patterns. So your lens that you're using to image that object with has a region of support. Okay, this is the parts of the original spatial frequency spectrum it would measure. Okay, it can now also measure these bits of that spatial frequency spectrum on this order and these bits of that spatial frequency spectrum on that order. So it can get other parts of the spatial frequency spectrum into its region of support and see what's going on. And this is not an unusual effect. It's the moire effect. Okay, so here we have two grid patterns. Okay, they might be quite fine. You might have trouble seeing them. However, when you overlay them, right, you see a grid pattern which is at a completely different spatial frequency, in this case a lower spatial frequency. So you're using a sort of moire effect to shift higher spatial frequencies down into the region of support of your lens. Okay? So that's the way the super resolving sim system works. Okay? You have to do a bunch of maths to extract those, extract all that information. Okay? You use laser illumination to get higher contrast fringes out of your illumination. Okay? You need to grab up to 5 images for a given grid orientation. It depends on how you generate that pattern of light, that grid pattern. And you need to use multiple grid orientations so you no longer see the grid. So you get full coverage of all spatial frequencies in all directions. The other thing you need to do is you need to know the phase of the grid at each point in the image. Okay, so that's one of the things you need to try and extract from the data you measure. You then use Fourier analysis to extract all the different spatial frequency components and put them back to where they should be. Okay, and what you can get is a proper 2 times improvement in resolution compared to conventional imaging. Okay, and it has improved region of support for higher spatial, well, improved support within the region of support at higher spatial frequencies than Confocal does. So this is what your grid patterns might look like. So this is the grid we're using for just optical sectioning sim. We're using a lamp or an LED, right? If you were to slice it in X and Z through your focal plane, you see there's a grid pattern which is in focus in the focal plane, and it loses contrast pretty rapidly outside the focal plane. That's why you're getting optical sectioning there. Okay. If you take the same grid pattern and illuminate it with a laser, this is what you'll see. This is actually called the Talbot effect, where you see the contrast reverse and flip backwards and forwards. Actually, this has a bunch of different higher orders. Okay, so particularly it has three extra higher orders on either side of the zero. Okay. You can use a phase mask instead, and some of the systems use that, and that's what produces the sort of 3 orders I showed in the previous graph. Okay. So what does this do in frequency space? So if I take our 5 order, our thing with the Talbot effect, if this is our region of support for our imaging lens, we can bung those diffracted orders of our illumination in these strategic points on that function. And what the Moiré effect does is it shifts a copy of this transfer function to each of these points. Okay. So if we only had our 2 order sim, okay, this is what we would get. That's 3 grid positions, 3 grid rotations. It still has a missing cone, so its optical section is not so great. If we had the 5 order sim, we get a region of support which looks like this. Okay, it's pretty much the same as the region of support you get in your confocal microscope, but it's filling these regions, these bits out the edge, much better than the confocal microscope did. Here's some examples. We've got a system we built, Imperial. It's using a spatial light modulator to generate the grid patterns, so you can programmatically define those grid patterns and their orientation and their phases. Okay, this is what a bunch of beads looks like. When you look at the conventional image, this is what those beads look like once you've processed them to get that super resolved image. Okay, and this is the same system looking at a stained set of cells, and you can see here's our sim image, and that's a conventional image, and here are the comparisons in various different parts of that image between the super resolved and the conventional image. So you see revealing that improvement in resolution. This is some other systems, some results we got recently. This is looking at some double stained cancer cells. Well, actually, these are wild type. We're really interested in looking at the cancer cells. The red stain is labeling parts of the chromatin, so the material that chromosomes are made out of. On the left, you can see what that image looks like as we change the position of our grid illumination. We're taking 5 separate images this is for one plane and one grid orientation, 5 separate images. You don't see a lot going on. You can actually see there's some very small features, and those are blinking on and off. Okay, and it's that blinking on and off, effectively, is one of the things that the analysis looks for or is looking for, and from a section from data like this, it can generate images like this. Okay, so what we're interested in is the red is showing us where the chromatin is. Actually, these are chromosomes in a cell that's been dividing. Okay, and the green is labeling certain protein domains within the nucleus which are important in cancer. Okay, so just to show you that as a, I think it should. So just showing you that effectively scanning through in Z, you can see it gives you super resolution in X and Y and Z. Okay, so why are we interested in doing that? So this is actually a project we've started about 6 months ago. It's our Brexit benefit project. Okay, just get it in before we leave the EU. It's all about trying to profile single cells in a high throughput environment. Okay, so it's actually this down here is we're making the crux of it is we're making little chips. Well, our partners in Milan are making little chips, and we're building a structural illumination microscope system within that little chip. It's a lattice light sheet, so that's a structural illumination combined with what's called selective plane illumination. So we're illuminating the object from the side with a thin sheet of light, and then we're putting structure in that thin sheet of light. Okay, And the idea is to do all this inside little chips here, so you can flow single cells through. You can take images of those, you can process those images downstream, and try and work out whether the cells you've got are cancerous or not cancerous. Okay, and that is supposed to be able to fit into part of the one big cycle of looking at therapies and developing new drugs for treating cancers. Okay, so this is an EU-funded project. It's future and emerging technologies, so they're things which are high risk and may or may not even come off. Okay, so just to summarise, I can see we're getting quick summary of how we compare those different wide field methods. So what are called wide field methods: spinning disk versus optical sectioning versus super resolving SIM. Spinning disk and optical sectioning, you can both do those with light bulbs or LEDs. A big advantage of spinning disk is you can take, it requires two images, but you can take them simultaneously. So it's not susceptible to motion. Okay. Super resolving, it requires laser illumination. You may need up to 15 images per slice. You end up with quite a large amount of data. It's probably of the order of 10 gigabytes, that 50 frames stack before it's processed. The big advantage of super resolving SIM is you get better resolution than conventional, better resolution than confocal. Okay? All of them get better axial resolution than conventional, but these two, because effectively we want to keep the grid contrast high, we back off on its spatial frequency, and we don't get much lateral resolution enhancement. They're all susceptible, though, to noise and photo bleaching. Okay, so that's a big problem. This one's not susceptible to motion. How about fluorescence versus bright field? So I've shown you a mixture of fluorescence and bright field images. Fluorescence is great. You can label structures according to their function, biologically or chemically. Another big thing, as a physicist, it's great because fluorescence resets the incoherence in the system. Okay, it's like we're shining light on it. It starts, it's reset the coherence. Point sources look like point sources again. Okay, bright field, on the other hand, is a partially coherent imaging system, right? And that means you don't necessarily know what you're going to get out of it. It's difficult to understand. You can use other contrast mechanisms, such as polarization and phase contrast, to get you better contrast out of these things. Photo bleaching is a problem, and there are not many photons in fluorescence. Lots of photons, no photo bleaching in bright field. Okay? Big one, sections in reflection or transmission. Nobody ever does transmission confocal microscopy for fluorescence. Okay? It's too difficult. Because you have to align things. If you do it in reflection, everything's automatically aligned. Chromatic aberration could be a problem. Bright field sections in reflection, but very importantly, it doesn't section in transmission. Okay. Just the final one, some future challenges. High throughput. These things can generate a lot of data. So perhaps this talk is not so much about what microscopy can do for the cloud and the data processing you can offer, but what the cloud and the data processing can do for microscopy. Some of the things we're having to look up now is we're doing a lot of processing on HPC systems, for instance. So speeding up analysis, machine learning techniques for image processing, okay, just trying to do things according to what the book says is not necessarily the best thing. We're also finding computational imaging techniques like deconvolution are getting easier and better, and they're starting to compete with optical techniques. But you can use the two together in combination. Another question is, can you do super resolving SIM with a spinning disk and make it faster? Well, maybe you can. And the final thing is, it's not had a chance to talk about these other things we do here. True resolution techniques. So none of these techniques will push you beyond that region of support increase by a factor of 2. Okay? You need to look at other techniques like localization microscopy and stead and resolved. So this is actually also a structured illumination technique. this is in a way, it's a funny technique. You're putting structure into your sample by making things turn on and off at a given time. Okay, so just finally some acknowledgements. Thank you very much.
We've definitely got time for plenty of questions, and also after this finishes, there's drinks and things outside as well. So don't run away. Questions set.
You had these 3 blue lines where the shifted Fourier spectra are overlapping. Can you tease these apart by, if the disk is rotating, the middle one is not rotating in phase, but the other one is rotating clockwise and the other one counterclockwise in phase? Is that a
Well,
way
they both
of-
rotate. They both rotate clockwise.
Okay,
Yeah.
but is this the way how you resolve them, how you tease them apart?
So this is for. You're talking about these ones.
That image, yeah.
Okay. So the way you tease these apart is you shift the grid pattern. Okay. So if you shift the grid pattern by a phase phi, this one shifts by phi, and this one shifts by minus phi.
That's what I
Okay.
meant by
All right. So in a way you're rotating them in complex space.
Yeah.
Yeah. And that's how you tease them apart.
So I really love Matt Gustafson's paper, but I'm thinking like why Rainer Heinzmann is never cited as inventor of SIM, especially his paper came 1 year before.
Well, actually, yeah, Rainer Heinzmann's has made a massive contribution. So, there's, for instance, even these results were taken using a Zeiss-Alira SIM system. Rainer Heinzmann helps them develop the software which does the analysis. So, a lot of the clever analysis was done by Rainer Heinzmann. A lot of that software analysis was done by Rainer Heinzmann. I'm not sure why Rainer. I think Rainer does get a lot of benefit of.
Yeah, I've never seen a talk on structured illumination mentioning Rainer's name. Especially his paper came 1 year before Gustafson, so.
Yeah.
Just wondering why, like.
I'm not sure if it's so. Maybe Gustafson also built a lot of ideas up on doing things non-linearly with non-linear.
Even the non-linear paper from Rainer came before Gustafson.
Yeah.
It was in 2002, and Gustafson published in 2015.
So actually, they all came around the same sort of time we did our optical sectioning sim. So Rainer Heinzmann was a student at that time,
Yeah.
I believe.
You mentioned a few times about pinholes and the SLM. And how small are these pinholes? Is it hard to make them?
Okay, so the good thing about optics is you can magnify images up until they're relatively big. Okay, so even if you were to take, say you took 100 times objective lens and you used the normal microscope, right? Your point spread function size might have a diameter of 250 nanometers. Okay, so 100 times bigger than that is 25 microns. Okay, but even then you can put another lens in and you can magnify that even larger, and you can get something which becomes very much more easy to handle. So a lot of commercial systems with pinholes, they're probably millimeter sized.
Oh, cool.
I can ask one last, if allowed. Yeah, okay. So again, a general question, like, so you mentioned about Minsky, you mentioned about Petran and spinning disk, and I'm thinking why Confocal never got a Nobel Prize.
Why did Confocal never get a Nobel Prize? I'm not really sure. I wonder who you might give it to.
Minsky, Petran, and Brad Amos or Breckenhoff or whatever.
Colin Shepherd.
Or Tony
Yeah.
Wilson, whatever.
Yeah. I'm not sure. And it's maybe they have to wait a few years before another one comes around in microscopy, and it was waited until it came around to super resolving techniques like Stead and Storm that they gave them out. So I think it's possibly because you have to have made like a big impact in other areas of science or technology or society before they award Nobel Prize. Okay, and because the growth of confocal microscopy started quite slowly, and maybe that's why it never made it.
Like in Cambridge, like when you hear like when Brad Amos was here, I heard it was an instant hit, right? In '89 when you saw such great enhancement in resolution. So I don't think it was a slow evolution of confocal like.
It was.
Yeah, we can talk later.
Yeah, I think it's probably a way to. It's because it took time before they, every lab had one. But having said that, our storm and stead is certainly not a simple technique, and and even storm is that's you can find that relatively easy, but that's there's a lot of people doing it, but even some of the inventors of that poo-poo it now. They don't like it.
All right, perfect. Well, thank you very much, and if we can thank Mark again, and as I said, there are drinks and nibbles outside around the corner. So thank you.